Hi everyone, welcome to Gateway Lectures. Here are the solutions for the quiz day 12, and today's subject is metal cutting basics or the theory of metal cutting. Right, here we have our first question. The details of an orthogonal metal cutting operation are given below. Right, the rake angle was 8 degrees, chip thickness ratio was given as 0.35, undeformed thickness, nothing but the T1 uncut chip thickness is given as 0.5 mm. Cutting speed is given as 3.3 meter per second, and the mean thickness of the primary shear zone is given as 20 microns. The shear strain rate during the operation is, we need to calculate the shear strain rate during this operation. Right. So in the question, given data is alpha, that is rake angle given as 8 degrees. Chip thickness ratio is generally denoted by R, that is given as 0.35. And the undeformed thickness is given as T1, that is equal to 0.5 mm. And the cutting speed is generally denoted by V, and it is given as 3.3 meter per second. The mean thickness of primary shear zone, we'll know what exactly is mean thickness of the primary shear zone, what exactly is primary shear zone in our next slide. See, here we are our general cutting of a workpiece having some thickness, and this is a T1 is the uncut chip thickness or undeformed chip thickness. Here we are seeing the green zone here. This green zone is called as primary shear zone, where the most of the heat energy goes in, where we do work to break the crystal structure of the basic material. For this material here in the primary shear zone itself, we spend 70 to 80% of our energy in cutting to break the crystal structures. That is our major part here, primary shear zone. And also in the primary shear zone, in the question it is given as mean thickness of primary shear zone. If we will draw them, first of all, the primary shear zone separately here. This is our primary shear zone. It is a zone actually. Generally for analysis purpose, it will be taken as a line. And how this zone will change in the course of time we'll observe here. And in the question it is given the mean thickness of the primary shear zone. This is the mean thickness of the primary shear zone, and it is given as 20 microns. Right, it is given as 20 microns. And in the time process, what happens is as the cutting tool pierces into the workpiece, as the chip starts breaking at the shear zone, the crystal structure keeps on breaking at the shear zone. Due to the dislocation, what happens is this shear zone thickness will be keeping on increasing with the time. In the next, see here, initially it will have some primary zone here, and next the shear zone thickness will be reduced, and so on. It will be reduced, and finally it will be into line. And once when it is into line, it breaks off. This is the mechanism how the primary shear zone helps in the cutting or helps in the break of the chip, breaking the chip. So this all happens in the primary shear zone. Okay, so in this way, and if you can observe here, it is having some thickness, and next the thickness is being increased, and again it is being increased here, and finally it is being increased here if you can observe. So as with time, this thickness is keeping on increasing. That increment is generally, suppose if some distance is increasing with time, then we can state one term called as velocity. So but here, since it is a shear zone, we term a component called shear velocity, and it is nothing but the rate of, simply we can write it as the rate of change of thickness T shear, the rate of change of thickness with respect to time. Right, this is our V shear. Understood? And in our question we are asked to calculate the shear strain rate. We know what is exactly strain is. Strain is change in length per original length. Suppose initially at the start of cutting it is having some original length, and in the course of time it is increasing its length, so it is changing its length. So it is changing its length with respect to original length, this gives the strain, but they are asking the strain rate. So with respect to time, how the strain rate varies. Understand? With respect to time, how the strain rate varies, because here as the metal tool pierces into the workpiece, the metal's ability will be deteriorating to resist the tool, okay, with time. So in that course of process, the stress acting on the shear zone is not a constant value, it is keeping on increasing. If it is keeping on increasing, then the strain also will be keeping on increasing with time. Strain also will be keeping on increasing with time. So we will calculate what is the shear strain rate. Since we are making here shear zone, and also strain is calculated for the shear strain, we need to calculate the shear strain rate. And always whenever it is given a rate, we can shear strain rate we can generally given as velocity of shear upon the thickness of the shear. Okay, this is the formula for shear strain rate. How can we calculate thickness of the shear strain? So if you can observe a triangle formed here, this is our TS, I have represented by the thickness. This is our straight line, it is represented TS, nothing but the thickness of the shear zone, and this is our uncut chip thickness T1. If you can observe here, this is a triangle formed, okay, and this angle here is given as phi, and here we can apply sin phi. Sin phi is equal to T1 upon Ts. From this we can get the value of Ts as T1 upon sin phi. Okay, for all this we need to calculate first what is phi here. So for calculating phi from the given data, we know tan phi is equal to, this is a general formula. You have to remember some few basic standard formulas for theory of metal cutting, then any problem will be easy. Even when you are sleeping, if you are waked and you are asked with this formula, you should be remembering this one. This is a very important formula. Tan phi is equal to r cos alpha upon, nowhere derivation is not that important for these formulas. So tan phi is equal to r cos alpha upon 1 minus r sin alpha. So we will substitute. R is given in the question as 0.35 and cos of alpha 8 degrees upon 1 minus 0.35 into sin of alpha sin 8 degrees. This in generally in gate examination how we will perform the calculation is, initially we will enter 8 and then we will apply sin to that, and then we will multiply it by 0.35 and then we will multiply it by minus 1 and then we will add plus 1 to it. Then we will apply inverse of this, nothing but there will be option called 1 by x, we will apply that. Then this complete value will be getting into numerator. Then we will multiply by cos 8. Then we will multiply by 0.35. Then we will get the value of tan phi. And the tan phi value we are getting it as 0.36434. We need to learn some tricks while applying calculations in the virtual calculator. That will be very important for gate examination. Tan phi we got, from that we will be getting the value of phi, nothing but tan inverse of 0.36434, and that comes out to be 20.0187 degrees. So phi is obtained. Now we'll substitute the phi here in the next in the formula of shear thickness, that is equal to T1, the undeformed thickness or the uncut chip thickness were given as 0.5 mm. So it is 0.5 upon sin of, the value of sin phi is 20.0187, and this shear comes out to be, thickness of shear comes out to be 1.46059 mm. And also in the question, in the question the velocity was given, that is the cutting velocity was given, and this was our cutting velocity here. There are three velocities in our complete metal cutting. One is the cutting velocity denoted by V, and other is the chip velocity, mean the velocity of chip with respect to the tool surface or the tool rake face, and also the V shear. Here we discussed what is V shear. So there is a relation among these three velocities. We need to remember that relation. That is very important. There are few basic formulas that we need to remember for metal cutting. Derivation is not that important for this, only formulas were enough. And the relation is V upon ultimate cutting velocity upon sin of 90 plus alpha minus phi is equal to V shear, nothing but velocity of shear upon sin of 90 minus alpha, that is equal to velocity of chip upon sin of phi. Okay, here we know the value of V, we know the value of alpha, we know the value of phi, we know the value of alpha here also. Then we will calculate the Vs. By equating these two equations, we will get the value of Vs, and the Vs comes out to be 3.341123.831 meter per second. I have taken a long value because we will be performing this complete calculation in the calculator itself. So let it be the long values to get the accurate answer. So we got the value of Vs, we got the value of Ts, and here the Vs value is in meter per second. So we will convert into mm per second, because our final strain rate will be having a unit of per second. Okay, and that will substitute here, the value of Vs will substitute here 3.341123.831 into 1000 to convert into mm per second. Upon the TS we got it as 1.46059, and from that we'll be getting our answer for shear strain rate as 0.22875 into 10 power 4 per second, and that is our answer for the first question, nothing but the strain rate. Hope you would understand how we got this formula, right? This is our answer. This is in this way we need to, while we are learning the subject itself, we need to learn the concept in such a manner that even in the examination, if you don't remember the formula directly, we should be able to drive this position Vs upon Ts, because tan formula anyhow you have to remember. And coming to the next question, while turning a cylindrical bar, the maximum allowable feed is 0.2 mm per revolution, and at this feed rate Taylor's two-life equation is given as Vt power 0.25 is equal to 75, where V is the cutting speed in meter per minute and T is the tool life in minutes. The labor cost and the overhead cost, actually both will be the same, is rupees 8 per minute, and the regrinding cost is rupees 120 per regrind. On an average it takes about 2 minutes to change the tool. Okay, the tool changing time was also given. What is the ratio of cutting speeds for the maximum productivity to the cutting speed for the minimum cost? For this question we need to learn the economics of machining. That I am also uploading today a video on this in the concept series, all complete details of economics of machining with the derivations. You can see there, you can practice the derivation once or twice to remember the formula. Even suppose in exam, if you don't remember the formula directly, within minutes you can just derive the formula. It will be very easier. Okay, and you can watch the derivation there. I will proceed with the formulas what I have derived there. You can watch that video and you can apply that to here. And first of all, I'll write the given data. Vt power n is equal to constant. The n value is given as 0.25, and also the capital C was given, the constant of tool life equation was given as 75, and the tool changing time generally will denote it by TCT. It is given as 2 minutes, and also the regrinding cost was given Z2. I'll generally denote the regrinding cost by Z2, and it is 120 per regrind of each tool. And also on an average it takes about 2 seconds, and the Z1 was given 8 per minute. Generally the labor cost will be per time. Suppose you get an operator, if you have to pay him, you need to pay the wage per the time he do. Suppose he is doing a 6-hour shift, then you need to pay hourly basis, or you need to pay for the 6 hours. Okay, generally the labor cost or that overhead cost will be per minute, per time. And the regrinding cost, there will be a separate operator, and for the performing the machining there will be separate operator. Changing the tool and perform the machining there will be separate operator. So that is why the regrinding cost is generally taken as separate, and for regrinding we need a grinding machine, and there will be a cost involved for grinding machine. So each time when we are doing regrinding, we give a separate cost for regrinding. And here Z1 is given in the question as rupees 8 per minute. I am not denoting rupees, you can understand here. So it is rupees 8 per minute. And in the question we are asked to calculate the ratio of cutting speed for maximum productivity to the minimum cost. So we need to calculate the V optimum for the maximum productivity to the V optimum for minimum cost. So we will calculate each of them individually. We will get the final answer ratio here. We will write the final answer here. So let's proceed to that. First of all, we will do for the maximum production. So we will calculate the optimum speed for maximum production, and you can observe, you can derive that in the derivation there. I am directly here writing out the formula. V optimum is equal to the constant of Taylor's two-life equation by 1 by n. N is the index for the Taylor's two-life equation. 1 by n into tool changing time and the complete whole power n. Why we and generally tool changing time is denoted by TCT. Okay, and we know all the values. C was given in the question 75, and the n was given in the question 0.25. Into the tool changing time was given in 2 minutes, and whole power n is 0.25. By substituting this, we will getting the value of V optimum max as 47.92 meter per minute. And also we will calculate the V optimum for the minimum cost. Generally, when we are performing the maximum production rate, what we will do is to increase the production rate. In the less span we need to produce more number of products. So what we'll do is we'll neglect the regrinding. We'll not do the regrinding actually, because if we are doing regrinding, then you are spending some time on regrinding, right? And you need a separate operator to perform the function. And if you are spending some time on the regrinding, suppose in an hour the tool fails for 4 times in an hour, suppose, then the 4 times you need to regrind it. Instead of using a new tool in the place of regrinding, then it helps in increasing the productivity. So in the maximum production rate, we will neglect regrinding. These all things I have discussed there in that concept series. You can just watch them. And here V optimum minimum cost, and the V optimum minimum cost will be writing the formula. It is C upon 1 by n minus 1 into TCT. Till here it was same as for the product 1, and here we'll have one more term plus Z2 upon Z1. In the minimum cost, we will not neglect the regrinding cost and the whole power n. Only the extra term is the Z2 upon Z1. And here we'll substitute the values. The C was given as 75 upon the 1, n was given as 0.25 minus 1 into TCT was 2 minutes plus Z2 was given as 120 upon the Z1 was given as 8 and the whole power 0.25. And this V optimum comes out to be 28.065 meter per minute. Okay, we got the value at the maximum production rate and value at this. Now we will substitute them in here. The V optimum max production, we got the value as 47.92, and that upon the optimum minimum cost, we got it as 28.065. Taking the ratio, it comes out to be 1.707. And this is our answer for the given question. Let's proceed to the next question. Question number 3. This is an interesting question and easy question. Mostly these type of questions will be asked in BARC. Even I've seen few questions on this were asked in BARC exam also. There will be nothing tricky in this. You need to understand the logic here. A standard machine tool and an automatic machine tool. So there were two machine tools actually. One was the standard machine tool. Tool in the sense a device, let it be a device. And the other is a automatic machine tool. Tool are being compared for the production of a component. So we are producing a same component on each of these machine tools. The same component is being produced, and the following data were given. The setup time. So for setting up, we need to attach all the tools here, or else any mechanisms to be attached here, and also the depth of cut and the feed, everything should be given. Okay, when we are making this operation. So for that setup cost on the standard, nothing but a conventional machine tool, it took 30 minutes. Whereas in automatic, it took 2 hours, because in automatic we need to load the software also. Automatic means mostly it will be involving computer, right? And also many sensors, actuators will be involved. So we need an extra time to set up. After setting up, the machining time per piece in the standard time, it is taking 22 minutes to produce one machine component. But in automatic, it is taking only 5 minutes. That is a very good thing. And the other thing is machine rate. This is generally the amount we pay for the operator for working per an hour. Suppose he is setting up the machine, he took 30 minutes. Then for the 30 minutes, we need to pay 100 rupees per him, since 200 per hour. Here it is taking 2 hours. We need to pay 1600 rupees for the same operator to set up an automatic machine tool. But when we are coming to the production of a machine component, in 1 hour, the operator can produce, on a standard, he can produce 2.72 components. Nothing but 2 components he can produce on hardly. Whereas automatic machine tool, the operator working on automatic machine tool, after setting up, he can produce around 12 components in 1 hour. We are having a higher production rate in this value, but we are having more cost for the operator. Since it is an automatic machine tool, we are having more cost. And here in our question, they are asking to make this automatic machine tool very useful, in the sense to make it very use of it. The main advantage of it, this is this 5 minutes time. You can say we can produce a more number of components. Thus, on producing a lot size, suppose 2000 or 3000 components, then this will be the more economical thing. If you were to produce 2000 or 3000 on this, in 1 hour you can produce only 2 components. If you were to produce 2000 components, then you need 1000 hours of time. 1000 hours you need to give rupees 200 per hour. But here, if you to produce 2000 components, you need only 16 hours. Here you need 1000 hours, you need 16 hours. So 16 hours paying 800 is very beneficial, very advantageous to the manufacturer. So here we need to calculate the value at which this automatic machine tool will be more economical. We need to calculate the value of number of components to be produced, where this becomes more economical. So what we'll do is in these type of questions, we'll make a break-even analysis. For that, we'll calculate the total cost. So we'll assume one thing. For producing, we'll make a statement here. For producing q number of components, you can name it of anything, but here to make it easy, I'm making a statement. For producing q number of components, so we'll calculate the total cost for producing q number of components on standard machine tool, and also the q number of components on automatic machine tool. And what we will do is we'll equate the total cost of both of these. Since suppose if it is for 10 components, it is taking some 3000 rupees, and at the same time for 10 components, if it is taking the same 3000 rupees, then after 10 components, this will be most economical, automatic, right? Because the time will be very less and it will be most economical. But after 10 components also, it is less compared to this till 10 components. So for 10 components, but here not exactly 10 components, it will be the economical. We'll make the calculation. So for producing q number of components, we'll assume that at q number of components, that both total costs are being equal, and after q number of components, the automatic machine tool is more economical. So for that, we'll calculate the total cost on the standard machine tool. So how will you calculate the total cost on the standard machine tool? First of all, the total cost involves two types of costs here in this type of machine tools. The one is machine setting cost plus machining cost. Both were different actually. Machine setting means the setting time we need. So here in our machine setting cost, it was given we need 30 minutes to set the machine. 30 minutes means 30 by 60, half an hour. Into, for that half an hour, we need to pay the operator 200 rupees at the rate of 200 per hour. So we need to pay 200 rupees. And also the machining cost, suppose for producing q number of components, and each component here we are said that we will be producing in 22 minutes, nothing but 22 upon 60. For this total time, we need to pay rupees 200 for the operator. This is the total cost for the standard, and the same for the total cost for the automatic. We'll make it automatic. So I'm writing auto here for automatic. Here also we'll have the machine setting cost and also the machining cost. And here the machine setting time was given as 2 hours. So for 2 hours it takes for machine to set up, and for the 2 hours we need to pay the operator, and the operator charge here is 800 rupees per hour, and also the machining cost here. But here the advantageous thing is for producing q number of components, for each component it takes 5 minutes, nothing but 5 upon 60. For this total number of components, total number of time, we need to pay 800 for the operator. Right. Now we'll equate both. TC standard, total cost at standard machine tool is equal to total cost at automatic machine tool for q number of components. Break-even analysis we'll do. Here q was unknown, here q was unknown. On substituting both, equating these both terms, we'll be getting the value of q as almost close to 225. So at producing 225 components, we are getting an economical condition on the automatic machine tool. After 225 components, we'll check how it will be. Suppose we got a 225, now we'll check for 230 components, I suppose. For 230 components, what will be the cost involved? 30 upon 60, half into 200 is 100, plus q is nothing but we assumed it as 230. So 230 into 22 upon 60, right, that into 200 per hour. Nothing but we are getting 16,866.67, and on adding this to 100, we will get it as 16,966.67 rupees for producing 230 components. The same, this is for 230 components. The same for the 230 components on the automatic. We'll check it on automatic. Initially the setup cost is 1600, and 230 into 5 minutes per each component divided by 60 into 800 for the total cost, and that comes out to be 15,333.33, and that when we add with the setting cost, and this comes out to be 16,933.33. You can observe here, comparing the cost, our automatic machine tool is consuming less cost than the manual. So this is the exact question to be understood. And going to the next question. This is a record of number of identical components produced at different speeds and feeds. These questions are very common. Whenever you see such type of questions, always remember we need the Taylor's two-life equation here. Okay, and that too, Taylor's two-life equation when feed and depth of cut are not constant. Okay, that we'll go through the question. Estimate the number of components that can be produced at a spindle speed of 310 rpm and also 0.15 mm per revolution, and the feed was given. So here there was a table at every spindle speed and every feed with some tool. They are with some component they are producing 311 and 249 and 144. These are the given. So what we'll do is we'll use the Taylor two-life equation when the feed and depth of cut were not constant. So generally the Taylor's two-life equation was Vt power A, F power B and D power C is equal to the capital C. This is when the feed and depth of cut were not constant. So here generally there is no data of depth of cut, so we'll assume it to be constant. So we'll remove the term since it is not varying. So we'll remove the term depth of cut here, and also we'll make one more statement here. Here depth of cut is removed, and here there is nothing about tool life, but there is a term called number of components. Suppose with the same component we are producing with the same spindle speed and with the same feed, if you are producing 311 components, after producing 311 components our tool fails. So instead of taking tool life, here they gave the count of components. Here they gave the count of components, and we will let that be some value here, let that be some denotation here. We will take it as C1. Okay, let that count of component be C1, and the V we know, V is equal to pi d n upon 1000. Therefore the V is directly proportional to the spindle speed n. So we'll rewrite this equation, this total equation as n, nothing but in place of speed. In the tool we have taken the tool life, we consider the count of components. So it is C1 power A it is, and F power B, and there is no depth of cut here, so it is equal to the constant. This is our final equation, final condition for the given situation. This is the final condition. Now at each point, let this be point 1, let this be point 2, and let this be point 3, and what we need to calculate is point 4. So at first we will calculate at point 1. At the point 1, 250 rpm was given, and the feed rate was given as 0.1, and the number of components is given as 311. So we'll substitute that 250 into C1 power A, nothing but 311 power A, into F power B, 0.1 power B is equal to constant C. We'll apply natural log on both sides. Apply natural log on both sides. Then we'll be getting as ln 250 plus, just to calculate A, B, C values, we'll apply log on both sides because A and B are in the powers. So A ln 311 plus B ln 0.1, and that is equal to ln C. Let this be equation number 1. Similarly, we'll take at equation number 2. The conditions were given 250 rpm, and the feed rate was given as 0.125, and the number of components was given as 249. Similarly, we'll apply that, and after applying log, we'll get it as ln 250 plus A ln, here 249 components, plus B ln, here feed rate is 0.125. That is equal to ln C. This is equation number 2. Similarly, at 3, the condition 3, it was given in the question as 300 rpm, and the feed rate is 0.125, and now the number of components is 144. Similarly, after applying the log, we will be getting as ln 300 plus A ln 144 plus B ln 0.125. That is equal to ln C. So we have 3 unknowns here, A, B and C. We have the 3 equations here. By solving 1, 2, 3, you can solve that on the calculator easily. By solving 1, 2 and 3, we will get the values of A, B and capital C. The small a value we are getting it as 0.333, and the small b value we are getting it as 0.3318, and the capital C value we are getting it as 787.46. Now at the stage 4, that is what we at the stage 4 we were asked to calculate, right? We can just write the final equation here. N C1 power 0.333 into feed power 0.3318, that is equal to 787.46. Here N, we need to calculate the value of number of components here. N was given in the question as 310 rpm. This was given for 310 rpm, and F was given in the question as 0.15 mm per revolution. We need to calculate the value of C1. So once we substitute the values, and we get the values of C1 as 75, close to 75 components. So we need to produce, with that condition we can produce 75 components. Okay, and this is our solution to this question. Next we are moving on to our last question, nothing but question number 5. In this question, it is an orthogonal cutting experiment was done with an HSS tool. And HSS tool, the tool signature terminology was given. The tool terminology was given on the ORS system as 0, 10, 7, 7, 10, 75, 1. We'll discuss what it is. And the depth of cut was given in the question. Generally, depth of cut will be denoting it. Sorry, width of cut is given in the question. It is denoted by 3.6 mm. And the depth of cut was given in the question as 0.25 mm. And the coefficient of friction mu is given as 0.7. That is nothing but equal to tan beta. From this we will get the value of beta, and that comes out to be closely 35 degrees. And also calculate the minimum power required at a cutting speed of, the cutting speed was given as 150 meter per minute. We need to calculate the minimum power required here. So first of all, what we can get from the designation? From the designation, for our question we need the rake angle, nothing but here it is an orthogonal ORS system given, so we need to get the orthogonal rake angle. Orthogonal cutting, we need to get the orthogonal rake angle. We'll see what all the specification denote. 0, 10, 7, 7, 10, 75, and the last is 1. I'll just speak out what all the values is. The 0 is called as the inclination angle, and generally for orthogonal cutting the inclination angle is 0, right? And 10 is called the orthogonal rake angle. That is what the data we need to get from this question, that is alpha is equal to 10 degrees. And here the 7 is the side relief angle, and the next 7 is the end relief angle, and here the 10 is the end cutting edge angle, and here the 75 is called as approach angle, and generally this approach angle is 90 minus of side cutting edge angle, that is CS. Okay, that is CS 75 approach angle, and the 1 is the nose radius. So from this question we need only this data alpha is equal to 10 degrees. We have all data was known. We'll proceed into solving the question here. So first what we will calculate is, we'll apply Merchant's first law analysis here, because this is an orthogonal cutting. We don't know the value of thickness or anything here. They gave our parameters here. So we need to calculate the value of shear angle here. For calculating shear angle, we'll apply Merchant's first angle analysis. We'll apply Merchant's first angle analysis, and what we got from Merchant's first angle analysis is phi plus beta by 2 minus alpha by 2 is equal to 45 degrees. And in the question phi was not known, we need to calculate. That is equal to 45 minus beta by 2 plus alpha by 2, and 45 minus the beta we calculated, we got it as 35 upon 2 plus alpha we have taken from the designation is 10 upon 2, and from here we will be getting the value of 5 as 32.5 degrees. So 5 is obtained. Next, what we need to calculate to proceed to the power. For calculating power, we can write power is nothing but force into velocity. But what exactly here force and velocity is? Here the force is the cutting force and the velocity is the cutting velocity. Cutting velocity was given in the question, but cutting force was not known. Then how can we calculate the cutting force? For that, they gave the shear stress value here, shear strength value. So by using that shear strength tau, generally the shear strength tau is written as nothing but shear force upon area of shear. And we know area of shear from the diagram of that we've taken in the first question here. In the first question we've taken this diagram. From here the width will be assumed as width of will be assumed as b, and every parameter will be taken phi, and from there we'll be calculating the shear area, and that shear area comes out to be b t1 upon sin phi. So here it is fs upon b t1 upon sin phi. Okay, here in the question tau was known and all the b t1 sin phi were known. We need to calculate the value of fs. So fs we can write it as tau into b t1 upon sin phi, and the tau in the question was given as 460 megapascal, nothing but 460 Newton per mm square, into the b value was given in the question as 3.6, and the t1 value direct value was not given, so the depth of cut is taken as the uncut chip thickness t1, and it is the 0.25. Okay, and substituting this 0.25 upon the sine of phi is we calculated sine 32.5, and from here we are getting the shear force value as 770.5198 newtons. And generally we will note the merchant circle. From that we will take a resultant and analysis. We will apply cos rule. We will get the relation between F cutting and F shear. So I am writing the direct relation. You can remember this. So from this, F cutting can be written as F shear upon cos of phi plus beta minus alpha and into cos of beta minus alpha. Here Fs was known, phi was known, beta was known, alpha was known. We can substitute all the values to make the calculation. We'll be getting the value of Fc as 1299.69 newtons. That will take it closely to 1300 newtons to make our calculation easier. And now we will calculate the minimum power required. We know what is the power required. Force into velocity. Nothing but the force is your cutting force and the velocity is the cutting velocity. Generally we denote it by capital V instead of making a subscript C, because C we will be making subscript for chip velocity. To avoid that confusion, we will be making a capital V here, capital V. And in our question the capital V was given and Fc was known, 1300 newtons. Just now we will calculate it, and the V was given in the question as 150 meter per minute. We will convert that to meter per second by dividing it by 60. Then that comes out to be 3250 joule per second, nothing but watt. Newton meter per second, nothing but joule per second, watt. And the answer is 3.25 kilowatts. This is our final answer for the question number 5. In this way, all the theory of metal cutting can be done. Theory of metal cutting is a basic subject for the machine tools. After knowing theory of metal cutting, then we can attempt all the questions in machine tools, because machine tools, it is our application of this theory of metal cutting. Here in theory of metal cutting we discuss about the types of reference systems, the types of tool designation systems, and also all this merchant analysis. So these questions are very actually easy. You can just practice all the formulae, then it will be very easier. And every year you will be getting one question based on these calculations. Every year you can see one question with this formula. Sure, you will get sure shot one question, because every question starts with this formula itself to calculate the value of phi. Or else if phi will be given, we need to calculate value of alpha, or else we need to calculate the value of t1 or the value of r. So in this way we need to remember these formulas, and every year there is a possibility we will be getting question on this economics of machining. This you can watch the video in the concept series today I have uploaded. This is all about this today's question quiz. Thanks for